So I'm going to talk about the issue of these accelerated reference frames. So let me do it like this. So this is some kind of a short summary. But the essential idea in here is that we just assume this existence of these idealized reference frames as called the inertial reference frames. Well, we just define them as like the frames in which the Newton's first law is valid, but I mean, in essence, all of the laws of physics, whatever they are actually valid in these inertial reference frames, okay? But since at this point, we just know the Newton's laws of motion, we don't know anything else yet. So we are going to see the law of gravity later, Newton's law of gravity. And then next semester, we are going to, well, essentially see the laws of electromagnetism and things like that, right? So in any case, so we basically say that all of the, I mean, we basically state all the laws of physics in inertial reference frames. That's what we should be doing. And we can check a frame is inertial or not by just checking the Newton's first law, right? Let's just say it like this. So in itself, this also implies this principle of relativity as well. It basically tells you that if a frame is moving with constant velocity relative to an inertial reference frame, it is also inertial. So as a result, I mean, all of the things that we say about this relativity and things like that will be is valid because of this. But that's a separate issue, right? That's relativity. In any case, and then we have these non-inertial reference frames. So these are frames that are moving with an acceleration relative to an inertial reference frame. So as a result, they are also called accelerated, okay? So that's just an alternative name, accelerated reference frames. I mean, sometimes I just say accelerated, okay? These are synonymous, they mean the same thing. In any case, so in accelerated reference frames, it might happen that some of the laws of physics might be valid, like the Newton's third law in here. It's basically this action-reaction principle, right? Because in an accelerated reference frame, the forces have the same value, right? Forces are not relative in a way. Okay, in those cases, of course, let's just say that I'm assuming that the directions of X, Y, Z are still the same and we're not in rotating reference frames. But if we are in rotating reference frames, things get a little bit more complicated, right? I'm just going to consider a situation where the origin of the reference frame is moving or perhaps accelerated with respect to the other one. So in any case, the definitions of forces and things like that is going to be the same. So as a result, Newton's third law is satisfied, for example, in an accelerated reference frame. So it is possible that some other laws are also satisfied as well. I mean, there might be some check marks in here, but there are lots of laws of physics that will be unsatisfied, right? So I'm just going to show you why these two are not satisfied. In any case, so it is also, I just wanted to say that, for example, the laws of electromagnetism is also, yeah, they are invalid in non-inertial reference frames. Especially the law, I mean, it's basically part of ray optics, but we know that optics is electromagnetism because light is an electromagnetic wave, right? So we know that, for example, one of the laws of these ray optics is that a light ray moves along a straight line. Okay, well, everybody knows that. So that's true in inertial reference frames only. In accelerated reference frames, it just appears that the path that followed by light will actually be curved, for example. So as a result, this is one example of a law which is not about the laws of motion. It's something else, but it is invalid in an accelerated reference frame, right? Let me just mention this. But there are other things like reflection laws will still be valid in those frames as well. In any case, so, I mean, let's just talk about these. I'll be talking about these, but in any case, what happens is that in here, we just have some kind of a trick. It's called a fictitious force trick. This is a trick that we somehow mentally add to these things, which basically makes the first and the second law valid. So it basically changes these two into check marks. But the problem is that well, it just makes the third law invalid, right? In any case, there's a price that has to be paid in here. So I'll be basically explaining this fictitious force trick in here, okay? All right, so let me just try to measure this. So I'm just going to assume that we have a reference frame in here, okay? So that's O. I'm going to assume that this is inertial reference frame. And then I'm going to assume that there is another frame in here. Let's say a bus frame where the frame is accelerated, okay? So I'm going to call this as B. So that's an accelerated reference frame. Reference frame, which means the acceleration of B relative to O is non-zero, okay? For this one, I'm going to use single letters for things which are relative to the inertial reference frame. So let me say it like this. I don't know, let's say RP, for example, is going to mean that it's the relative to O, for example. So as a result, I'm going to do this. So suppose that I have some kind of a particle in here, right? And this particle has some forces acting on it. So that's F1 and F2 and whatever. So I know that for this particle, I don't have space left in here. So let me, yeah, I think I'm going to do it like this, okay? So let me move this somewhere in here. All right, let me also make this like that. In any case, I'm going to write the equation like this, right? The sum of all of these forces, F1 plus F2 plus ... let's say that Fn, right? I don't know. I mean, there might be some other forces acting on these. Let me call this as Fn is equal to mass of that particle times the acceleration of that particle, right? So that's Newton's second law. So that's basically is in, right, O frame, because this is the acceleration relative to O. Okay, and let's just remember that if I mean, accelerations, all accelerations have the same value in all so let me say it like this. If I is another inertial reference frame, then I know that the acceleration of the inertial reference frame relative to O is equal to 0, which then means that the acceleration of the particle relative to that frame, by the definition, is like the difference of these accelerations. So therefore, this is AP. So which means the acceleration of an object has the same value in all inertial reference frames. Okay, so that's the important point in here. I mean, if I pass to a different reference frame, the forces are going to be the same. So the net force is going to be the same. And if that different frame is also an inertial reference frame, the accelerations would be the same, so that therefore the left and right sides are not different from each other. So as a result, this equation will still be the same in all inertial reference frames. Okay. So just keep this in mind. And so as a result, what I do is, yeah, let me just draw this thing again. Okay. So let me pass to the accelerated reference frame now. So this equation is still valid. So let me squeeze it in here. So I can still write this thing down like that. So F1 plus dot, 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 Fn, that is equal to mass times the acceleration of P. That's still true. But I would like to express this as an acceleration relative to B, but in that case, that's not true, right? We know that that's not true because I know that this is basically equal to mass times acceleration of P minus mass times the acceleration of the reference frame. Okay, so I know that the sum of all of these, well, this is basically equal to the net force, so therefore these two sides are not equal to each other. So what I would like to do is to basically make this equation right. In that case, that's what I do. I mean, let's just write this thing down like that. So that's mass of the, mass multiplied with the acceleration. Sorry about that. Let me write MP in here. Plus MP times the acceleration of the reference frame. So as a result, this is the form of the Newton's second law. Newton's second law in accelerated reference frames. Okay. I mean, the difference in here is that, well, this is not net force is equal to mass times the acceleration, all right? So this is the acceleration relative to the frame that we are in, but these are not equal to each other, and these are not equal to each other. So therefore, F equals ma is not satisfied, but it is satisfied in that form. If I add a second term in here, this is satisfied, okay? So as a result, I have to modify Newton's second law. Newton's first law is also modified. You know that if the net force is equal to 0, then the system does not have zero acceleration. So when the net force is 0, the acceleration of the objects is not equal to 0. So you will have to say something else in there, okay? In any case, okay, so the trick in here is to move this term to the left-hand side, to the size of the forces, and keep the right-hand side as mass times acceleration. And so as a result, if I actually count this as some kind of a force, in that case, this Newton's second law appears to be valid, right? So as a result, this is basically something like that, right? And then we have mass of the particle multiplied with the minus the acceleration of the reference frame. So I'll talk about this in a moment. I'm just going to explain a little bit more. Okay. So I mean, in that form at least, yeah, let me box this and then I'm going to remove the box in a moment. In that form at least, so if I count this as some kind of a force, but it's just an imagined force, in that case, we have all of the physical forces in here, plus this imagined force. So together with this imaginary force, the Newton's second law appears to be valid. Okay. It just appears to be, but I mean, it's just, we're just fooling ourselves, right? All right, so that's the trick basically. So in any case, let me add this in here. So these are all real forces. So this has an imaginary force. Imagined force. in any case, the correct name in here is fictitious force. Okay, so that's called the fictitious force term. So if I add an imagined fictitious force to the forces, then in that case, in an accelerated reference frame, the Newton's second law appears to be valid. Okay, so in any case, so that's the fictitious force. All right, so let's say acting on a particle. Let me say thought to be, right? Thought to be acting on. So the definition is that this fictitious force is equal to mass of the particle multiplied with the negative of the acceleration of the reference frame. So let me explain again. So that's the mass of the particle. So that's the negative of the acceleration of the reference frame. Okay, so that's perhaps confusing because to compute the fictitious force, I have to somehow bring together the properties of two different things. One is the mass of an object, and the other one is a property of the reference frame. It's not an acceleration of the particle or anything like that. It's the acceleration of something that's unrelated to the particle. It's the acceleration of the reference frame. Okay. So let me answer these philosophical questions at the end. But I mean, let me repeat that this is something that we imagine. It doesn't exist actually, right? So by a force, we mean the real forces. I mean, the things like when you push a wall, for example, you're applying an actual force in there. This is not something which exists, right? It's a quantity which has the dimensions of force. Nobody applies such a force. It's a result of a physical interaction. Just remember that the forces are due to because of the fact that the different particles are interacting with each other. And we know that there are these four kinds of forces, like these electromagnetic force and gravitational force and things like that, okay? So there are four mechanisms in nature for applying a force. This is not one of them. This is something which is just imagined. It's just a product of our brains, right? It has nothing to do with the particle, nothing to do at all. We just add this just so that our F equals ma equation appears to be correct. Okay, let me actually state it like this. So I'm just going to give you one example in here. Yeah, let me just come back to that check mark in here, okay? So if I add this fictitious force, right? The second law, somehow, I made it correct. So if I also include this fictitious force on the first law, so as a result, together with the fictitious force, the net force is equal to 0. In that case, within that reference frame, the objects seem to be not accelerating. Well, they are not accelerating within that frame. So you can also correct this. But this time there's a problem in here because we know that all physical forces have these, they come with these pairs of forces. I mean, if two of them are interacting, forces are applied on each one. But the fictitious force is just a product of our imagination. It doesn't have any action-reaction pair, right? So as a result, somehow the third law appears to be invalid if you just think of the fictitious force in that, right? So as a result, I mean, there's still a problem in here. And of course, there are still problems about the laws of electromagnetism and things like that, right? So you appear to correct some of the laws of physics, Newton's first and second. Let's say that Newton's second law is corrected in a way, but it's just corrected in appearance only, right? So again, you should keep this in mind. If you don't have to, don't use accelerated reference frames, don't use them. But in some cases, it might be actually easier to think, to analyze some certain problems in accelerated reference frames better than the other frames. So I'll be solving some problems specifically for that purpose. Okay. So I'm just going to solve a few problems in here, right? So that's a problem. Sorry. I'll start with the simplest problem. Okay. So the problem is this. I have a, I don't know, let's say 3 kilogram object in here, no friction. No friction. Okay. And we are pulling this with a force towards the rightward direction, which is, let's say, it's just a number like 33 newtons, for example. And the question is, what's the acceleration? Acceleration of the block. Okay, so we will solve this problem. I mean, we just start with the simplest problem, obviously. So in any case, let's just say that this is just the inertial reference frame, but there are these two other reference frames in here where we might be actually viewing these. So I'm going to suppose that there is some kind of a person in here inside a bus, let's say. So that's, yeah, inside a bus. So that's a bus in here, right? I'm going to call this as a B. So it's accelerating, let's say, towards right with an acceleration of 2 meters per second squared, okay? And then let's say that there's a car in here, perhaps a Jaguar. Let's just call this as a J reference frame. And let's say that this is accelerating towards the left with an acceleration of, let's say, 5 meters per second squared, okay? So in any case, I'm going to solve the problem, the acceleration of the block, in these three reference frames. So let me call this as the O reference frames. So O is inertial, B is accelerated, and the Jaguar is also accelerated. The bus and the Jaguar, they are accelerated. The ground frame, the O, is the inertial reference frame. Okay, so we'll be basically solving this problem. This is just for illustrating what's happening in here. So in O reference frame, right, O frame, this is the free body diagram. Okay, we have the real force acting on it, so that's 33 newtons. This is a 3 kilogram object, obviously. M is 3 kilograms. As a result of this, this has an acceleration. Okay, and it was supposed to be blue, so let me make it blue, right? So I always drew this as with the blue color. So in that case, we say that, well, F equals MA. So force is 33 newtons, and the mass is 3. So therefore, A is equal to 11 meters per second squared. So that's basically relative to O. Did I say? Yeah, let me call this as P, okay? So that's the object P, let's say. So that's the acceleration of P. Okay. I mean, let's use the correct terminology in here. So by acceleration of P, I mean the acceleration of P relative to O, but that's also the acceleration relative to any inertial frame. So as a result, in all inertial reference frames, the acceleration is 11 meters per second squared. So from the bus frame, okay. So let's just remember that the bus was actually moving towards right. Right, this was something like that. All right. Yeah, let me draw this in here. Sorry about that. So in the O frame, the bus was accelerating towards right. Okay. So within the bus frame, the free body diagram is going to look like this. So there is a real force in here, which is 33 newtons. And then there's a fictitious force. This time, this fictitious force is acting towards left, and its magnitude is given as the mass of the particle times the acceleration of the reference frame. Okay, so in any case, so in this case, the fictitious force is mass of the particle is 3, and the bus was accelerating with an acceleration of 3 meters per second squared. So therefore, this is 9 Newton and towards the left. Okay. So in the reference frame of the bus, the box basically appears to look like this. So therefore, as a result of that, the particle, the block, whatever, has an acceleration relative to that reference frame. Let's say that it is towards right. And so therefore, F minus F fictitious is equal to mass of the particle, mass of the box, multiplied with mass of P, multiplied with its acceleration, right? So that's the Newton's second law in that frame. Again, let's remember that this force is real. This force is just fictitious, it's imaginary. So as a result, the net force is 11 minus 9, sorry about that, 33 minus 9. Mass is 3, so I need to solve for this. So therefore, this is 24. So therefore, the acceleration of the box is equal to 8 meters per second squared. Shouldn't we say minus AB? It depends on which frame that you're using. I mean, if I'm talking about the, I don't know, the X component, if I have define an x-axis, yes, that would be something like that. So as a result, let me try to explain it like that. So if I have chosen the x-axis like that, then the acceleration of the bus relative to, acceleration of the bus has an x component which is given by plus 3 meters per second, in which case this fictitious force in here would have, by using the same x-axis, would have a value which is minus mp times ab. So that's going to be equal to minus 9 newtons, right? So as a result, if the x-axis is pointing rightward, in that case, the fictitious force has a negative x component. So if that's what you mean, then yes. But when I was solving that problem, I didn't specify any axis, so I wasn't actually doing these. Okay. I don't know if that solves your problem. Okay. So, I mean, if I had chosen the x-axis like that, right? In that case, this is negative then. So that should be actually the x component in here. So that would be positive in that case. The fictitious force is towards left. Okay. So in any case, in some cases, I don't want to use these axes and things like that. Let me erase all of these. I mean, let's just use this in magnitude. So AB is like 3 meters per second. So as a result, this picture is correct because we know that the bus is accelerating towards right with that acceleration, 3 meters per second squared. Okay. And this picture is correct. The fictitious force is towards left with a 9 Newton magnitude. Okay, so both of these pictures are correct. So I somehow incorporated this minus sign as a property of these vectors. So I know that the fictitious force as a vector is opposite to the acceleration of the bus. So I just drew the direction and then wrote the component of the force along that direction. Okay. All right, so that's basically what we are doing. So is this force acting on the box? No, it isn't. Basically, the box has nothing to do with the bus. All right, so that's the original picture. Box is outside. It has nothing to do with the box. What happens is that somebody in the bus frame is looking at that box and observing it from her own reference frame. This is an inertia reference frame, so as a result, that person shouldn't use that reference frame. So it's a mistake to use that frame, but to cover up that mistake with a small trick, she adds an imaginary force to the set of forces. So in addition to the real force, she supposes that there is some kind of a fictitious force acting on the box. With this addition, somehow the Newton's second law gives us the correct acceleration, right? You can easily check that this is the correct acceleration because we have already found that the acceleration in an inertia reference frame, in O reference frame, so it was already 11. So the bus's reference frame is 3. So we know that this is 8 meters per second. So this checks. So it gives us the correct one. So let me again do this from the Jaguar's reference frame. Okay, let's just remember this. Jaguar. So it doesn't look like a Jaguar, but next, whatever. So the Jaguar is accelerating towards the left with an acceleration of, what did we say? 5 meters per second squared, okay? All right, this is, I think I should, sorry about this. This is actually confusing, okay? So this is Control X. Let me erase this. So this is O reference frame, right? From O reference frame, things look like that. So that's the O frame. So within the O frame, the Jaguar was accelerating towards left with an acceleration of 5 meters per second squared. In Jaguar's reference frame, it appears that Jaguar is not accelerating. Let's say Jaguar is at rest. Okay, so there is an observer inside Jaguar who is looking at that box by just, I don't know, turning behind perhaps, just looking at that box. So that person is going to see that there is a real force acting on it towards the right. There is also a fictitious force acting on it, which is towards right. So it's basically mass of the box multiplied with the acceleration of the Jaguar. So that's going to be 3 times 5, so that's 15 newtons, right? So the person in the Jaguar is going to say that, well, because of that, the box is going to have an acceleration towards whatever that direction. To find the acceleration, he just needs to add these real force and the fictitious force. It's the net force basically, and then that has to be equal to that. So this is 33, that's 15, so that's going to give us 48. So that's 48. 48 divided by 3 is 16. So as a result, this is 16 meters per second squared, APJ. And we'll check that this is also correct, okay? In any case, I mean, this is basically what we do, right? So the fictitious force has nothing to do with the acceleration of the object or the motion of the object. It just depends on the mass, but it's basically some imaginary term that's added to actually make these equations correct. Okay. Again, why the third law is not valid? Because, I mean, this thing does not have any action-reaction thing. Why is this important? Because Newton's third law is related to one of the fundamental laws of nature called the conservation of linear momentum. When we talk about the linear momentum, we will come back to this. So the third law is actually quite essential for that purpose. So as a result, this actually makes the picture. I mean, it makes this fundamental law of mechanics invalid, right? Conservation of angular momentum is also somehow is based on the Newton's third law. So it appears that the Newton's third law is even more fundamental than the Newton's second law, because I don't know, I mean, we actually, when we pass to relativity or quantum mechanics, we see that the Newton's second law is somewhat modified, but the Newton's third law are still valid in these kind of situations as well. So it's a little bit more fundamental. I mean, if we have time, we're going to talk about this. So as a result, this is a big mistake, a big problem with this. So what I said is at the beginning is still true, right? Don't use this unless, of course, there are some special situations where it has to be used. There are things like things happening inside a bus. So when you are traveling with a vehicle, I could have said the same thing for the International Space Station, okay? But I'll talk about the International Space Station as well. But I mean, I know that most of you have ridden buses and you have experienced this thing. So when the bus is accelerating, okay, I mean, what happens in here is that you actually see the outside, but you never imagine that you should actually use some outside place as your reference frame. You naturally use the bus as the reference frame. So as a result, I mean, this is something that you cannot help it. So you naturally use the bus as a reference frame. Okay. So in any case, in this kind of a situation, I mean, let's say that the bus is speeding up. In that case, I mean, from this reference frame, therefore, what happens is that there has to be some kind of I mean, from that reference frame, you can actually understand things better if you assume that there is a fictitious force acting on you, pushing you backwards. In reality, what's happening is that, well, nobody is pushing you backwards. It's just that the bus is accelerating in the forward direction. So as a result, you have some kind of an inertia. You want to move, you tend to move with a constant velocity, but the bus is not moving with constant velocity. So the velocity of the bus is increasing. So as a result, relative to you, the bus appears to be moving forward. So as a result, you just leave behind, actually. Nobody is pushing you behind. But I mean, what you experience is as if something actually pushed you behind. So as a result, you just fall back. Okay. So as a result, I mean, you can also observe the things happening inside a bus by using this fictitious force concept. You can use it, but you know that you never feel anything. You never feel that somebody's pushing you. But what you experience is as if something actually has pushed you in the backward direction. How is this problem solved? Which problem is solved? So this is inertia, basically, right? I mean, from an inertia reference frame, that has a very simple explanation. It's just inertia. But again, the problem is that this is the problem, right? So when you are inside the bus, your mind somehow takes the bus as the reference frame. And so as a result, things appear to be accelerating in the backward direction with no apparent reason at all. There's no apparent reason as well. What's happening is basically the bus is accelerating forward, but your mind doesn't think like that, right? So in these kind of situations, I mean, you can analyze these kind of things by using this fictitious force concept as well. Okay, so in any case, so let's say it like this. So this is the forward part of the bus. I think I need to give a break, but let's say it like this. So the bus was moving like that. So let's say bus suddenly brakes. Okay. So in that case, the acceleration of the bus is in the backward direction. Right? The velocity is towards right. Acceleration is towards left. In which case, the fictitious force on you would be in the forward direction. Yeah, let me put a vector sign in here, okay? So bus suddenly brakes and it pushes you in the forward direction. Or bus is taking a turn, in which case, let's say bus is turning left, let's say, in which case the acceleration of the bus is in the leftward direction. And so as a result, the fictitious force should be in the rightward direction. Right, let's talk about this. Let's talk about this later. Let's take a break in here.